dissipated by the lightning bolt, does that happen where it reaches ground or where it hits a tree, or is this occurring over the entire
It's occurring over the entire air gap. It's heating up the air throughout. And of course, when it hits the ground, that current also flows through the tree or whatever, and it can also heat up that particular item. That's what we see. But it had to heat up everything in between as well. Okay, what is a capacitor? Let me construct a basic capacitor for you up on the board. Capacitor will be a device that has two connections, like a resistor. A resistor has two ends to it. A capacitor has two ends to it. Inside a capacitor, those two ends are not touching each other. There might be two metal plates on the inside, one metal plate here, one metal plate there. And what happens if you try to apply current onto the capacitor? So if I somehow put some current going in, that charge that's flowing into the capacitor can't go through, can't go from this plate to that plate. Instead, what it will do is that charge that flows onto the capacitor will start to pile up on that plate. So if I push positive charges onto the capacitor, positive charges will pile up on that plate. If this was part of a circuit, maybe connected to some kind of battery, if I have a current I here, I'd have the same current there, the same current there, same current there, same current there, same current there. So those positive charges that are piling up on this side of the capacitor have to be leaving the other side of the capacitor. And as they leave behind negative charges on the other side. A capacitor is kind of like a parking lot. So you could have a road, and normally for a road or a highway, the number of cars entering the highway has to equal the number of cars leaving the highway. Assuming all the cars are driving down the same highway, there's no exits or anything like that. However, a capacitor is kind of like a parking lot. There can be current going in, but there's nothing going through. It kind of just fills up this parking lot. So current going onto a capacitor is going to start to fill that up. And it's not like, what's unlike a parking lot is that once you put the first car in the parking lot, if the parking lot has 10 spaces, putting the second car in there is not very difficult. In this case, what happens is each extra charge you put on here gets harder and harder and harder to put on there. Putting the very first charge onto the capacitor is free. It'll just pop right on there. Putting the next charge on there is a little harder because a positive and a positive will repel. So when you put the next positive charge on here, it's like, oh, I don't want to go near that guy. So the two positive charges will go to probably opposite sides of the plate, get as far away as they can from each other. And now when I put a third positive charge on here, it doesn't want to go there at all because there's already positive charge there. It's being repelled by those positive charges. I put another positive charge on there. That got even harder. So each charge I put on the capacitor, I have to push harder and harder to get them on there. They don't want to go all crowd next to each other. Do you think it will be easier to put charge onto a capacitor if this plate is really small or if that plate is really big? Which one would you think would make it easier to push charges onto the capacitor?
big?
Really big, correct. Okay. So it will be easier to put more charges there if that area is big. We'll see where that area comes in a moment. I believe in physics class you have studied something called Gauss's law, correct? No? Not yet?
Is it called something else too?
No. Maybe not. Maybe not yet. Okay? No worries. We're not going to do Gauss's law today. However, I'm going to use a result from that. I do believe in physics class you are looking at charges, positive and negative, and you've introduced in physics class the idea of the electric field. You can calculate the electric field due to an individual charge. You can also calculate the electric field due to groups of charges. So I'm interested in the electric field in between these two plates. If I wish to get the electric field in between these two plates due to all those positive charges and all those negative charges on that side, that result will be easiest to get using something called Gauss's law. So I'll just write for now, from Gauss's law, and if you've never heard of Gauss's law before today, now you've heard of Gauss's law. So from Gauss's law, the electric field in between these two plates will be equal to the charge density on the plate. The symbol I will use for charge density is a sigma. That will mean charge density per area. If I meant per meter, I would use a different symbol. I would use a lambda. And if I meant per meter cubed, I would use the rho, just like we do in other classes for mass density. So the electric field depends on the charge density. More charges means a greater electric field in between. And divided by a constant, epsilon 0. Is electric field a vector?
Yes.
Yes, because it's force per charge. It tells you what the force would be. And since force is a vector, it's a vector. If I put a positive charge right here, which way would it tend to move?
Down.
Down. So what is the direction of the electric field at that point? Bless you.
Down.
Down. The electric field direction will be the same direction as the what force you have if you put a positive charge there. So in this case, the electric field is in the negative j hat direction. The electric field is a vector. Okay? Electric field is, now I'm going to rearrange this. Just bear with me a minute. I'll be done in 5 minutes and we'll be back to our good old capacitor relationship. I just didn't want to go any longer in the class without giving you some background what a capacitor actually is before we start using it in all of our formulas. I'm going to replace, so this comes right from Gauss's law. I'm going to replace the sigma with charge per area. And then that could be rearranged as charge over area times epsilon 0. And I'm going to replace electric field with a relationship between electric field and voltage. And we can figure out that relationship just looking at one of the units we've used for electric field. Electric field units, we've got two of them. Could be newtons per coulomb, or it could be volts per meter. So I can replace electric field. Again, here I'm not trying to introduce all the physics. Electric field could be replaced with volts per meter. So volts per that total distance here, which I'll call D. It's a lot like the example I did earlier with the ceiling. I had my 20 volts. So to get the electric field, how many volts per how many meters? The electric field would be volts per meter. Bless you. So I get voltage over D equals Q over A epsilon 0. Just two more steps. I'm going to solve this for Q. I'll go below it. Okay, solved it for Q. Now finally I want to take that relationship, and instead of having a relationship between charge and voltage, I'd like to have a relationship between current and voltage. So for a resistor, this key relationship that we used over and over again was V equals IR. That was the relationship between voltage and current for a resistor. I'd like to get something similar for a capacitor. What I've got now is Q in V. And while that might be fun and useful in some cases, I'd like to get a relationship between current and voltage. What should I do to both sides of this equation
Take the
that
derivative.
would take Q and turn it into a current?
Derivative.
Yes. Take a derivative with respect to what?
Time.
Time. So current is dq dt. So I'm going to take a derivative of both sides of this equation. So a derivative with respect to time of a epsilon 0 over d times v equals a derivative with respect to time dq dt. dq dt is called I, that's the current. This derivative, well, I can see which of these are constants. The epsilon 0 is a constant. The area, that area is the area of these plates. That's also a constant. D is the distance between the plates. So unless you're actually going inside this little capacitor and changing that distance, it's going to be a constant as well. So these are all constants, and I get A epsilon 0 over D times dV dt equals the current I. I'm going to call area of the plates times epsilon 0 divided by the distance between them. I'm going to call that clump of three numbers the capacitance. So I'm going to label that C. And the relationship that's left then is that I equals C dV dt. There's a lot here. I'm pulling in the idea of electric field. Some of you've got physics, but maybe fairly new in physics. I am pulling in actually two different definitions of electric field. One was this idea of force per charge. The second is this connection between voltage and distance. Okay? Both of those are valid relationships for electric field. We could talk for an hour about this. There are other problems with what I've oversimplified a couple things, but I don't want to do the hour version of this. I just wanted to do the 5 or 10 minute version. Let me just give you an example of one of the problems I haven't dealt with carefully. Electric field, vector or not a vector?
Vector.
Vector, correct. Voltage, vector or not a vector?
Not a vector.
Not a vector. Distance, vector or vector?
Not.
Well, if it's a distance or position, it could potentially have a direction to it. Could be, maybe, maybe not. So how on earth am I getting a vector from a non-vector and a maybe vector? How do I handle the division of two things? So if that's not a vector, why am I getting a vector here? How is that mathematically working out? If any of you are interested, I can talk with you more about that. But that's where, if I were to go into details like that, I'm going to get myself into the hour-long version and not the 5 or 10 minute version. So I'm just pointing out one of the things I've kind of glossed over here.